Hello, and welcome to the very last section of central limit theorem, binomial distributions, and this z-score business. From here on out, we're looking forward to a midterm coming up, and then we're looking forward to inferential statistics of the testing and regression sort to take up the last half of term. But we've got one last piece of binomial distribution, and we also set a little bit of a precedence for how this course will carry on in the future chapters, because we will find that we have a section that talks to us about the z-score, usually in terms of the population parameters. Then we'll tend to talk about scenarios when we don't have population data, we only have sample, and then we usually end each chapter discussing some form of probability binomial, P and Q, probability percent chance scenarios. So we had ended the last example, we had talked about some blood pressure data types, and we had mentioned it was very fascinating that as you have more elements of your sample, the sample becomes a much closer fit to what we expect the population to be doing. And we said blood pressure was very interesting because it was very cheap and very easy to get a lot of population level blood pressure sample data. So we could have both the sample and compare and contrast that with the population. Now, of course, we're looking at this piece that talks about binomial distribution. Recall our old binomial formula. The chance of having precisely R successes is going to be the combination of NCR, and we're going to have P to the R, Q to the N minus R. And this will give us our chance of exactly R successes. Now, in this section, we talk about the binomial distribution, which is the idea that we can create essentially a histogram that has in each of its, it's not quite a histogram, but still it's essentially a histogram, that has on each of its columns the chance of 0 successes, 1, 2, 3, and so on. And then as the height on the y-axis, we can have ourselves a probability measure, namely this one. And what you will find is as n gets large, regardless of what your chance of success is, as n gets large, as you move through the r's, the histogram will stop looking skewed and start looking more normal. It's a feature of binomial probability, up to a little bit of conversion factor. So recall, n is the number of trials overall we're going to do, and for fewer trials, you will have a probability histogram distribution that doesn't look very normal. But once R gets big enough, I think several examples in the book get all the way up, to 50 n, and I think anytime you reach over 50, 55 n, it starts to look highly normal, even for pretty strange probability of successes. R is the number of successes we want. Again, we can calculate each R using our formula, and then each R becomes a new column in the histogram. P is the chance of success, 1 minus P is the chance of failure. Again, I will repeat advice from earlier. Remember, success and failure don't necessarily mean what we usually mean them in everyday language. A perfect case example of this would be, let's say we're talking about cancer, and people can either have cancer or not have cancer, maybe. That's a binomial scenario, win or lose. But let's say we are cancer researchers. Well then, for us, if we're trying to find people with cancer to try our new drug on, that hopefully cures it, success for us is someone who has cancer. And that can be a little odd, because I would never say having cancer is successful if I met someone on the street. But if you and I are researching cancer together, then success very much is finding someone with cancer so we can cure it. So, chance of success, you can play with who gets what. What do you call success? What do you call failure? Keep in mind it's contextual, not this global definition of success that we normally have. The rule for the binomial distribution, though, is this, unlike when we're calculating single pieces. The total number of trials times the probability of success should give us at least 5 times when we have this success. So if we have, I don't know, there's a 30% chance of passing a class. Well, then you need to have enough people so that 0.3 times n gives you at least 5 people who pass. And on the flip side, you need to have n times q being bigger than 5 as well. You need at least 5 failures. If you don't have 5 and 5 on either side, the histogram won't really look normal. It won't pass the Pearson skew index, in essence, of accuracy, and it will be a little bit twisted, in which case you can't talk about normal probabilities. You have to calculate this all out differently. So we have this rule that you have to have at least 5 successes and at least 5 failures. If you have that, then you can calculate mu quite easily for binomial. Remember, mu, if you have yourself a whole population, you have to add up all the terms and divide by capital N. But for binomial, we know a lot more than just the idea of, if we have all these terms, we in fact know that we have either win or lose, success or failure. Consequently, it's a lot faster to calculate mu. It's also a lot faster to calculate sigma. It's much easier to get yourself an accurate measure for those. But again, this only works if you've got at least 5 wins and at least 5 losses. Then we have a continuity correction. If you're trying to measure your endpoints on a normal x-score scale for a z-score, we have to have this convention because of the fact that we're talking about discrete probabilities R. Keep in mind the word discrete is 1, 2, 3, 4, 5. There's no middle terms there, because we're talking about a certain number of successes out of a certain number of trial. It doesn't make sense to talk about 1/2 people succeed. You have to round that in some direction. But if you want to look things up on a z-score chart and talk about your x's, you have to do r minus 0.5 if it's a left point, so you stretch the left side a little more left by the minus, and you do r plus 0.5 to the right, adding that a little bit to the right, so you stretch it out just a little bit wider so that it can encompass this fact that we might have the difference between discrete to continuous random variables like we normally deal with. We have an estimator for p hat. Remember, we have the difference between sample and population conventions. P hat is a sample average. So you take the number of successes divided by the total number of trials, and this creates your ratio for the sample. P hat then becomes a good point estimator for the population percent, which would happen if n became very large. Thinking about the law of large numbers. Mu of p hat, the average, the population average that we expect if we were to average through all the p hats, we would expect that to average out to p, the population measure. And sigma of p hat. Remember, for our z-score, we had 2 different forms of z-score. We had both z was equal to x minus mu over sigma. This was for comparing a single element to the population, whereas we also had our z-score of x bar minus mu x bar over sigma x bar. This was comparing a sample to the averages of the populations, but remember we said this and sigma were the same because the average of the averages was the same as the average of all the points. And we said that sigma x bar is going to be the same as sigma divided by square root of n, where n was once again our number of elements in our sample. So this same process where we had these different z-scores here also lets us talk about calculating these in terms of binomial distribution, and we find out that sigma p hat, just like we had sigma x bar, is a little bit different. Sigma x bar is sigma over square root of n. Sigma p hat, the average of all the p hats, well, the deviation at least of them, is going to be pq divided by n, all under a radical. So these are our pieces that we're looking for. Rather than work a particular example, because of course your textbook has some pieces of that, I wanted to end this section by sort of chatting through some of the things that we can solve, maybe talking about them in terms of high-level descriptions. So this idea of binomial probability is that we would like to tackle problems that have chances of win or loss, success or failure, and try to measure this out. So I think maybe looking at the word problems in the back are interesting to consider. And if you look through them, you'll find that they talk about some rather interesting topics. So you can talk about the chance of before and after in different health scenarios. And I won't use their exact examples there, but let's say that in the past we used to use a certain additive in some drink. We decide that that additive is no longer safe. You could talk about the amount of drinks that had that additive before and how likely it was that we would have, for every 20 people who walk around and eat food in the world, What's the chance that only one of them's had that additive? And what's the chance that 2, 3, or 4 of them? And we could compare and contrast that now after we've gotten rid of it. What is it? I think it's BHP or something that we've gotten out of our drink containers because we don't like the plastic additive. Or you could be looking now, what is it, the state in the east that had recently had its water supply shut down because of a leak. Now I've just dated this video forever. So you can compare and contrast these sorts of things by looking at these calculations. I think that then wraps up, once you've worked through the calculations. In particular, look at the example in your book that intros binomial distributions. Also look at the breakout example that talks about continuity correction. Make sure you're able to do those calculations. I think this gets us to the point where we are done with the first half of term. So let's review just a little bit to put this all in context, what we've got, because somehow this all has to get crammed into our heads for the midterm, right? We started off term talking about what statistics was. Namely, it was this idea that we could somehow organize and interpret and consider and contrast and compare data. And we started out just by doing things like saying, what is a random sample? What type of samples might we have that are other than random? We talked about convenience samples and stratified samples, etc. As we progressed further on, we were able to do things like frequency distributions. We could take raw data and organize it. We also had the stem and leaf plots that were interesting so that we could try to organize raw data and see what does it look like. This is just sort of observational things. We're not doing any real interpretation. We're simply saying, can I get a handle? Can I organize this in some way? But then we moved a little further and we started being able to talk about these measures of central tendency. And so we had mean, median, and mode. And then we also talked about deviation. So we started to get a sense of not just overall how could I organize the data, but how could I have some sense of here's a collection of stuff, what describes it? Is my stuff very wiggly, or is the stuff a little more sedate? Do I have this collection of students who have high average scores or low average scores? What's a single number that I can use to describe this group of students? Or what can I use to describe the whole population as a whole for things like blood pressure or number of clicks on a website? Then we took a little bit of a pause and we broke into the next couple of sections that introduced some ideas of probability and counting. Because we have to be able to count how many of something we have if we're going to be able to take a number of successes and divide it by a total number of trials. What you'll find is that we sort of introduced those, and so we talked about permutation and combination. There were some differences between those. We talked about the binomial probability formula, so we could count that chance as well. And then we moved into this most recent section, which is where we finally started wanting to answer the question of, if your score is this, how do you compare to the population as a whole? How many people score less than you? How many people score more? Can we get 2 scores and see how many people do we expect to score in between this range? Can we have some cutoffs? That might be interesting. You could be interested in cutoffs for particular things. Let's say we have a scale that measures stress. And you could be very low stress or very high stress. And we happen to know that for a particular career, very low stress people, people who are all laid back and chill, don't come off as very go-getting in that career. On the other side, very high stress individuals also maybe aren't a perfect fit for this career because it's going to be too stressful for them. They need a career that's a little more relaxed. So you find a range in the middle and you find a percent. And you say, okay, now we get a whole bunch of applicants in, and we grab an applicant, we give them a test to see how stressful they are in general, and we compare their stressfulness to everyone's stressfulness and say, do you fit inside this range? And we start to ask ourselves the question, how many people do we have to interview to be guaranteed that we have at least 5 good candidates for the job? You know, how many people do we have to give this stress test to till we can get ourselves down to a short list of 5 before we pick which one of these folks is the best? So you can have that kind of thing that we're able to answer. Where we're getting ready to go from here is we're getting ready to look at a little more interesting aspect of statistics, which is inferential stats. This is going to be where we're going to take our let's say, sample blood pressure measure of just 20 people and say, well, that was 123 was the average high blood pressure. And from there, we're going to be able to say, well, can we figure out some way that that 20 people sample averaging 123 tells us anything about the 120 that we know is the population average? How do we make that inference? How do we estimate that? How do we calculate a range? That's where we're going. But before then, we have to be very good at the test, because we do have a midterm coming up. So again, things to remember and keep in mind for a midterm. It's important to practice a closed book set of testing. You have to be able to do a closed book, and if you haven't practiced without closed book, maybe now's the time to just start, get that happening. Other things to be thinking about for the test. It does no good to panic. And I don't say that from some kind of self-righteous place. I say that from a place of I have taken many, many tests in my life. I do not consider myself a good test taker in the past, but like everything else, the more practice you do, the better you get at it. And so even at test taking, the more practice you do, the better you are at it. So a practice test not only makes sure that you know all the things from the book when it's closed that you need to have in your head, but it also, of course, gives you this ability to, well, practice taking a test. And so then the real test isn't quite as scary. You can succeed. You can succeed at a midterm, you can succeed at a final, you can succeed at statistics. It's all about practice and telling yourself, you don't really need to stress about a test and during a test, because the worst that can happen isn't actually very bad. If you want some final pointers, I do encourage you to come to my office hours. I have chocolate as a general rule, and you should come and visit and ask questions, get answers, explore statistics, and be safe. I'll see you after the test.